Okay, so in the most recent lectures, we've been talking about bending. We have horizontal member acted on by vertical loads. Doesn't necessarily have to be like that, but the member will be stretched in one direction, the loads will be perpendicular to that. So we have transverse loading. Right, so we have our beam, and we have some type of loading acting in this transverse direction. And up until now, we've been talking about pure moment. So pure moment would be the case of putting a moment on either side. We have continuous moment across the beam, therefore there's no shear. There's no shear, there's just a constant moment. Today we want to expand our discussion a little bit broader to where we can have a changing moment across this beam, which is what you'll have if you have this distributed load. And we want to look at what that does to the shear stress distribution. We know that we're going to have some value of shear force at any point in this beam because we can make our shear diagram and compute that value. That then is going to get distributed along a cross-sectional face. And from what you know from the very beginning of this class, if you have shear stress on one side of a little cube of material, you must also have equivalent shear stress on the orthogonal side in order to keep this in moment equilibrium. So not only are we going to get shear stress in the vertical direction, but also in the horizontal direction, or longitudinal direction and transverse to the beam direction. So let's take a look at how we prove that this is the case.
So like on that graph, the transverse direction would be going that way?
Transverse direction is perpendicular to the beam, so in this figure it would be the vertical direction. All right, so if we have some type of loading on this beam, and it's creating a gradient of moment, so we have a non-constant moment. If we were to cut out a segment of that beam and look at it, say, from the side direction, it's going to have a bending stress on the left-hand side that looks like that. It's a varying bending stress, and that would be the sigma at some x value. And if we say that this distance is delta x, then there will be another bending stress distribution on the other side that corresponds to x plus delta x. Now, if moment is constant, these two will be equal, right? My over I won't change. But if the moment is changing, then even if y and I stay constant, you have different bending stresses on either side, which means this is no longer in equilibrium. So the way that we put it back into equilibrium is by saying that we must have some tau xy acting on this longitudinal side. And that's necessary to put it into equilibrium. So really what we're deriving is this longitudinal component of the shear, this longitudinal shear stress, and then from our knowledge of moment equilibrium, therefore the vertical shear stress must exist, or the transverse shear stress must exist. Now what you're going to see is that this distribution of shear stress, this tau xy, is going to vary depending on where we are in terms of y. So let's get this is our y-axis. Depending on where we are in terms of y, we'll have a different value of shear stress. It's a function of y. And when we have boards, so you might have seen this if you've ever played around with a ream of paper or any other type of stack plies of an object. If you apply bending to an object, you can see that those plies are disconnecting from each other. Do you agree? You see how at the ends they are moving relative to each other? So if in a material, however, the bonds between adjacent plies or adjacent molecules don't allow one portion of the beam to move relative to the other. So that tendency to want, I'll let you do it, a tendency to want to rotate or to displace relative to each other, that's because of the shear stress. But the material has some shear stress capacity that resists that shearing. And then eventually when you reach the capacity, it's going to break apart. But the bonds between the materials are what causes it to not have varying displacements of the ends.
So the shear stress causes it to do that, right?
The shear stress causes it to want to do that. Yeah, the shear stress is brought about by the fact that it's not allowed to displace. So like in between the plies in this scenario, there's no shear stress because they're just moving freely the way they want to. But then within each ply, so within this top member, there is going to be shear stress because that top member has to be moving together, right? This end right here is not having differential displacements. The other thing is that when we have a cross section, technically there's warping of the cross section when it's experiencing shear, but we neglect that in our analysis. So warping violates the assumption of plane sections remain plane. And the amount of warping is negligible in slender beams. So in this class and probably in most of your undergraduate education, certainly for civil engineering, we neglect this warping. Yes. It means that we assume that plane sections remain plane, so we don't concern ourselves with
Well, that's what warping means?
Yeah, so warping means that this cross-section doesn't stay the same cross-sectional shape and it doesn't all move perpendicular to your longitudinal axis. All right. So let's go back to that little element that we used to prove that we had shear stress. So remember I had sigma x on the left and sigma x plus delta x on the right. And then tau xy. Let's take the equilibrium, or let's look at the equilibrium of this object. So we're going to take the sum of the forces in the x direction and set them equal to 0. So before we do that, let's see, this comes from a bigger cross-section, right? The rest of the member would look like that. This portion of area, I'm going to label A prime. So if we're looking at the cross-section itself, this is A prime. Oops. Here's the center of our cross section. y, and z. Y prime is the distance to the beginning of this area that we're looking at. Therefore, C minus Y is the height of that area, that shaded area. There, now we can do our integration over this area, because this is the area that our normal stress is acting on. So we take our normal stress, sigma x comma y, which means that sigma is going to be different at both x and y. So we plug in the x, y that we're interested in. That gives us some stress value. We integrate that over the area dA. I'm going to subtract the integral over a prime of sigma x at x plus delta x, comma y. Integrate that over the area. And you know what, for consistency, I want to draw these arrows as compression. I'm writing my equations as if this is in compression. So let's make that clear. Good, then I have some shear stress, tau xy. And we're going to assume that the shear stress distribution is constant throughout the thickness B. So from side to side, we have a constant value of shear. So instead of integrating it, I can just multiply by B, and that's the width at y prime, because this may not have the same width at all elevations, but at y prime, it has some value of B. And then I'm going to multiply that by dx. Delta x is this value here.
And the distance we're taking is from our centroid, right?
The y prime value is measured from the centroid, correct. And this all has to sum to 0. So we can plug in for sigma x. We know that sigma x is negative m times y divided by I. So we integrate that minus the integral of negative m x plus delta x times y over I. Plus tau xy by prime dx, that all equals 0. So just bringing this over to the other side, or rather separating these terms. So I got my shear stress equal to the rest of it. So now this becomes negative. I'm going to pull out the moment, because the moment at a particular x value is constant. And I'm going to pull out the I, because that's constant. And that's integrated times y dA. And then that gets added to m at x over I times the integral of y dA. Okay, so note these both have this integral of YdA term. And it would be really nice if we could get rid of that integral. So we come up with this thing called Q. Q is specific to a Y value. On the same cross-section, for varying values of Y, Q will take on different values. And Q is defined as the first moment of area of the portion of the cross-section above Y prime with respect to the axis about which bending occurs. So first moment of area, as you might recall, the equation for that is area times a distance to the centroid. So A prime is the region that we're interested in, the region above which we want to calculate the shear stress, and then we multiply it by Y bar prime, where Y bar prime is the distance from the centroid of the overall cross-section to the centroid of A prime.
That's the one we were always adding in the T section, T shape thing, the AD squared, AD. When we're,
Yes and no. You're asking about a value of Y that we use when we are calculating I for the cross-section.
Yeah.
No, it's slightly different. In that case, we were looking at breaking the shape up into different areas. This is looking at a particular elevation and wanting to know what the shear stress is there. So if you're wanting to know what the shear stress is at the base of, say, the top part of a T section, then yes, it happens to be the same at that one location. But generally speaking, they're two different terms. All right, so there's a couple locations where we can look at this and know what the value of Q is. Okay, so if this is our cross-section, considering that formula I just gave you, what is the value of Q at the very top? 0, and why do you say 0? There's no area above that. Good. So here, Q equals 0. What do you think about at the very bottom? Okay, why do you think it's 0? Yes, Y bar prime would equal 0. So now when you talk about, when you're at the bottom, the area of the portion we're looking at is the same as the overall area. Therefore, the distance between those two centroids is 0. And the maximum value of Q, as you're going to find, is here at the centroidal region. So the centroid is where you get your largest value of Q. And this distribution ends up being parabolic. So you go from 0 to some maximum back down to 0. And if you look at our equation for shear stress, Let's carry this on to the next page. Everybody has that written down? Good. You can say tau xy is equal to m of x minus m of x plus delta x times q. We're replacing q of y prime. So we're replacing that integral term with q. We're dividing by I. And now in the way we had written this before, we had b on the left-hand side, but now we're dividing by b. And we're going to divide by dx. So you can see this is going to end up being a linear function of q, which means that if q is parabolic shaped with values of 0 at the top and the bottom and maximum in the middle, then your distribution of shear stress is going to have to be the same, where your tau max is going to happen at that centroidal region, and it's 0 at the top and the bottom of your member. Okay. We have a dx in the bottom of this function, which just makes it's begging me to take the limit of delta x equal to 0. And that gives us tau xy equals, okay, so the only things in here that are functions of x are the moment, right? If I have the moment at x minus the moment at x plus delta x, so this is a change in moment, and dx goes to 0. Now what happens when I have a delta moment and dx becomes very small? Has an m in it, but it's not m. What happens when you have a finite difference and then you make it really small? This? Yeah? Yeah. Yeah. Okay, but here's the catch. Here's the catch. Moment of x, or sorry, dm is the moment of x plus delta x minus the moment of x when you take the limit of x, delta x going to 0. But we have the opposite of that, right? So we want a negative. Good. We want a negative dm. And what is the derivative of the moment? What is dm? Excellent. It's the shear. So the shear times q divided by I divided by b. Now I shortcutted this a little bit. It's actually v times dx. That dx gets crossed off with the dx in the bottom, and we're good. We're left with this equation. So this equation is just as important as negative my over I. So put it right up there on your shelf with negative my over I. You want to know this formula.
So this has always been happening, but we just didn't know it.
Yes, we just haven't been talking about it. Yeah. All right. So negative VQ over IB. What that means is if you want to know the shear stress in a member at a particular point, you first need to do a shear diagram to figure out on that beam what is the shear force acting at the cross section. You then need to figure out, okay, where vertically am I interested in? Because that will give me my value of the width of that particular location, if the width is changing. Otherwise, it's one constant value. But it also gives you the value of Q. Q is a geometric property you can calculate based on the height that you're interested in. And then I is a cross-sectional constant. So 3 of these terms are geometry-based. The 4th is from statics, getting your shear from the shear diagram. Because 3 of the 4 terms are geometry-based, we can simplify this ahead of time for common geometries. So for example, we can look at rectangles. We have a lot of rectangular beams. We can look at what this value would be for a rectangle.
Like a general equation?
Yes, a general equation. And let's look in particular at the case of y prime equals 0, which means we're looking at our centroidal location, because that's where we're going to have the maximum shear stress. And so that may be a case in which we're considering frequently. So for the rectangle, we have Q I don't understand why it's fighting me. Okay, Q equals, the equation is y bar A prime Okay, so if we're looking at this shape, what is y bar? Well, let me give you B and H. So this is B, this is H. What is y bar? Half of H would be this distance. Is that y bar?
But the H over 2 minus 2.
Let's do H over 4. And then the next thing is A prime. So what is this area above the centroid? B times what? BH over 2. Good. Okay, so your Q is BH squared over 8. I, what's I for a rectangle? Good, 1 over 12 BH cubed. And then B, of course, is B. So therefore, tau max is negative V times Q. So we have BH squared over 8. Now we're dividing by I. So the 1/12 throws the 12 up top. We keep our BH cubed on the bottom. Multiply by B. Top B in the numerator and the denominator reduced to 1. H squared in the numerator causes the exponent of H in the bottom to go to a 1. Goes from 3 to 1. I have a BH on the bottom. What does that equal to?
The area of the thing.
Good, it's equal to the area. So I can just say negative V, well, actually let's deal with our constants first. 12 over 8 is 3/2 times the shear force divided by the area. Okay, so I want to make this very clear. I've given you a powerful tool here. When can you use this powerful tool? If your cross-section is a rectangle. That is the only time that this formula gives you your shear stress. What's the other condition? where does this give you the shear stress at? It's the maximum value. So it's at the centroid. So if you're asked for the shear stress anywhere else on a rectangle, or if you're given a shape that's not a rectangle, you cannot use this formula. But if you're given a rectangle and you're asked for the maximum shear stress, I highly recommend you use this, because 3/2 shear coming from your shear diagram divided by area is significantly easier than calculating Q and I, right?
And you'll have to get the shear at the center, right? Of that triangle.
Yes, this equation is to get you the shear at the Y value corresponding to the centroid. And then we assume it's constant across the width at that point. Okay, so for other shapes, you're not so lucky. For other shapes, you have to calculate Q. So another common shape that we run into is an I. These are very commonly used as beams. This vertical part here is what we call the web. These other parts are what we call the flanges. And if you're going to calculate Q, so say you want the maximum stress, which we know is going to happen at the centroid, so we're looking for that to be our A prime. You're going to calculate Q. You're going to need, let's see, Y bar times A prime, which now gets broken up into two components. So this is going to be Y bar 1, area 1, plus Y bar 2, area 2. Where I would treat this flange as area 1, and this small portion of the web, or half of the web, would be my area 2. It'd be similar for a T. When you're calculating these, if your measurement Y is up above the centroidal plane, that's a positive value of Y bar. If Y bar measurement requires you to go down below the centroid, that's a negative measurement. So you can get negative Ys. That's how it ends up decreasing as you go down below, is because you start having a negative Y.
So is the max at the centroid?
Yes.
Okay.
Yes. The maximum is always at the centroid, specifically because once you pass the centroid and start measuring downward, now you're subtracting. Q is decreasing because Y is negative.
Does it switch directions?
Does the shear switch directions? Not when you pass the centroid, no. Because it goes from 0 to a maximum back down to a 0. We will speak in future lectures about shear flow and directions of shear, because it does have a particular direction, but the centroid does not cause it to change direction. All right, so if we look at what's happening here on this cross section, let this vertical line just represent the cross section. So the flanges are up here and down here. We're looking now at the side of this member. That shear stress distribution, if we calculate it at varying points, we're going to get that it looks like this. You have these little tiny parabolas at the top and bottom, a big discontinuity because B jumps. B starts out big, and then it gets real little. And then this part also has a parabolic shape. And so what we see is that most of the shear stress is carried here in the web. Would you agree there's very little shear stress in those flanges? Yeah. And then, not necessarily relevant for today's lecture, but most of the bending stress is happening in those flanges. So your bending stress looks like that. So now those flanges are carrying a lot of bending stress. All right, so our web needs to be designed for this maximum shear stress, this V max, which we can get by calculating negative VQ over IB. And when you calculate that out, coincidentally, it's approximately equal to negative V over the area of the web. It's slightly less than this. So this will give you a conservative approximation of the demand. So this, if you calculate the negative times the shear from your shear diagram and then just divide by the area of the web, that will give you a conservative estimate of your shear stress. So those are two shortcuts.
Just the cross section that you drew.
Yes.
How exactly will this draw? Like from the right side, like looking at it from the side?
Are you asking me about this?
Yeah.
Yeah, I'm looking at it from this side. Trying to show you what's happening on this cross-sectional face. This one is, this is shear, this is sigma. Other questions? Yes.
How's the moment working on that? Is it working?
What does the moment look like? So the moment would be like that. Other questions? All right.